drum roll, the why do we care moment, the finale. Why do we care? Because it holds your DNA together. The electric force keeps our body together, and I'm going to prove it to you right now with this problem that shows that base pairs actually have a net attractive force that allows the spiral strands of the DNA to actually stay bound together. This is cool. Let's prove it. This is where physics gets really powerful, because the stuff that chemistry teachers and biology teachers have told you all this time, now you can actually say, yeah, and I know why. And I can calculate it. All right, let's do it. So we over here have, okay, I'm just going to read this. The two sides of the DNA double helix are connected by the base pairs. You guys know this. Adenine, thymine, cytosine, guanine. Because of the geometric shape of these molecules, adenine bonds with thymine and cytosine bonds with guanine. The figure shows the bonding of thymine and adenine. Okay, so you have thymine over here and adenine over here. Okay, thymine stuff, adenine. The figure shows the bonding of the thymine and adenine. Each charge shown, these are all plus or minus ions, right? So that's negative E plus E, negative E plus E, negative E. Okay, and you can calculate the net force that thymine exerts on adenine. Okay, so this is how I want to look at this. I want to say, what is the direction of the force over here on adenine as a result of thymine? Okay, so the way I see it, there's four forces here. What are those four forces? Well, I'm going to show you. We have a force of H, this hydrogen atom, due to oxygen over here. Okay, that force is definitely going to be in this direction, and I'm going to call that force 1. Okay, then we have the force of repulsion between oxygen and nitrogen, because they're both negative, right? I'm going to call that force 2. Okay, then we have this force of repulsion over here between these two nitrogens. So that's this. I'm going to call this F3. And then we have a force of attraction here between this hydrogen and this nitrogen. That's going to be that is going to be F4. Okay, so we want to know what the net force of F1 plus F2 plus F3 plus F4 is. All right, can we do this? Obviously, I wouldn't have you do this if we couldn't, okay? So let's take them one at a time. F1. What is F1? Well, again, all of these are electrostatic forces, so we're talking K, Q1, Q2 over R squared. All right? So in the case of F1, we have K, so that's 9 times 10 to the 9, right? Times, these are both just, a charge of 1. So, right, a charge of 1 electron, because these are ions of just plus and minus 1. So that's going to be 1.6 times 10 to the minus 19. And there's 2 of them, so I'm just going to go ahead and square it. Right, that's easy. Notice again, I didn't put the signs because I already took into account, I will take into account the sign based on the direction of the force. So we're going to call this direction positive and this direction negative. Okay, positive, negative. So this whole thing is just going to get a big negative in front of it, right? I did not have to put that in with the charges. I just used the vector itself to tell me what the direction was. And you guys should do the same. So you have this, and you divide by, what is the distance between these? Well, we know that the whole distance here, given by the problem, is 0.28 nanometers. And then this bond right here is 0.11 nanometers. That means this distance between them right here is the difference between those. 0.28 minus 0.1 is 0.17. Do I have that right? I believe so. 0.17. And it's nanometers, so it's times 10 to the minus 9 squared. All right, we can very easily solve this using things. I get a minus 7.97. I'm just going to say 8. 8 times 10 to the minus 9 newtons. Okay, that's my first force. 1 down. Piece of cake, basically just plug and chug. We need to have a picture of the direction of forces, but other than that, It's just a plug and chug problem. All right, so we have F2 over here equals, well, same problem. We have 9 times 10 to the 9 times 1.6 times 10 to the minus 19 squared. Again, it's two minus 1 charges. That makes that really easy. We already know the sign. It has to be positive because it's repelling, right? So, and the only thing that changes now is r, because that's the full distance between these two atoms, which is 0.28 nanometers. So that's 0.28 times 10 to the minus 9 squared. And for that, I get 2.94, I'm just going to say 3, times 10 to the minus 9. Okay? For F3 over here, that's going to be this fellow over here. And again, we're going to do the same thing. It's going to be 9 times 10 to the 9 times 1.6 times 10 to the minus 19 squared, all divided by, well, this is that full distance again, so that's going to be 0.28. Actually, no, this full distance is 0.3 here. So that's going to be 0.3 times 10 to the minus 9 squared. For that one, I get positive 2.56 times 10 to the minus 9. Okay. For F4, I'm running out of space, but I will just say this. It's the same exact thing, except from this 0.3, we need to subtract the distance between this bond, because 4 is just the force between this hydrogen and this nitrogen. All right? So the distance between them is 0.3 minus 0.11. All you do is you take the same thing, but now you're dividing by 0.19. And for that, I get negative 6.38 times 10 to the minus 9 newtons. Okay? All right. F1 is negative 8 times 10 to the minus 9. F2 is 3 times 10 to the minus 9. F3 is 2.56 times 10 to the minus 9. Make that 9 a little bit more clear. And then F4 is minus 6.38 times 10 to the minus 9. Let's add them all up together, like we said over here. I get, when I add these all together, negative 8.85 times 10 to the minus 9 newtons. I know this got crowded, but you can always pause the video, follow along, make sure you add these yourself, prove it, see if I got it wrong. But the bottom line is this. That is a negative sign, which means that the net force is towards thymine. What does that mean? It means attraction. So we just proved, using the basics of electrostatic physics here, that thymine is actually going to be attracted to adenine, and that is what holds these two base pairs together. And that's pretty cool. I'm going to leave you on that awesome note. Take care, and I'll see you next week.